At 5:09 in the morning, a camera installed in one of America's most visited national parks recorded something that had never been captured on film before. A dark plume of steam jetted out of the ground north of a thermal pool that had already exploded once less than 2 years earlier. Within seconds, three separate vents had torn open in the earth. A 61-foot fissure split the surface, filled immediately with water heated to 194 degrees Fahrenheit. Rocks were thrown across the landscape, and the Firehole River flowing downstream from the site turned milky gray with sediment. Nobody was there to see it, not because the park was closed, because the ground itself gave no warning that it was about to open up. Welcome to Biscuit Basin, Yellowstone National Park, one of the most geologically unstable pieces of land on the continental United States. And as of June 13, 2026, the site of the most significant hydrothermal explosion ever recorded on camera, occurring just 328 feet from a monitoring station that scientists had installed specifically because they expected something like this to happen again. They just didn't know when. And as of today, they still don't. To understand what happened at Biscuit Basin on June 13th, you need to understand what Yellowstone actually is. Not the park, not the geysers, not Old Faithful, which is less than 2 miles from where this explosion occurred. You need to understand the system underneath all of it. Yellowstone sits above one of the largest active volcanic systems on the planet. Its magma chamber, a partially molten reservoir of rock and superheated fluid, stretches roughly 90 kilometers long and 40 kilometers wide beneath the surface of Wyoming. Above it, a hydrothermal system of extraordinary complexity circulates billions of gallons of groundwater downward through fractures in the rock, where it is heated by that magma chamber to temperatures far exceeding the normal boiling point of water. Under the pressure of the rock above it, that water stays liquid. It moves through underground channels, pools, and conduits that humans have never mapped completely and may never fully map. And then, in certain places, it finds a weakness in the crust above it, and it escapes. That is a hydrothermal explosion. Not a volcanic eruption, not magma reaching the surface. Something more specific and in some ways more unpredictable. A sudden decompression event in which superheated water beneath the ground flashes instantaneously to steam, expanding with explosive force and ejecting whatever is above it. Rock, sediment, boiling water, into the air and across the landscape. USGS geophysicist Michael Poland, the scientist in charge at the Yellowstone Volcano Observatory, has described these events as violent and dramatic, resulting in rapid ejection of boiling water, steam, mud, and rock fragments. What he has also noted, and what makes them uniquely dangerous, is that scientists have not yet been able to definitively identify their precursors. The explosion at Biscuit Basin on June 13th happened with what the monitoring station recorded as only a very small blip in temperature data before it occurred. No dramatic warning, no escalating seismic signature that would have told observers to evacuate. Just a small anomaly, and then an explosion that split the earth open. This is the part of the Yellowstone story that 4.5 million annual visitors do not fully reckon with. The geysers are predictable. Old Faithful earned its name. But the hydrothermal field that feeds them is not an orderly system. It is a pressurized network of superheated water moving through fractured rock, and when that equilibrium breaks, it breaks without notice. At 5:09 a.m. on June 13th, monitoring equipment at Biscuit Basin registered seismic energy and infrasound, low-frequency acoustic signals, coming from the direction of Black Diamond Pool. The camera installed in 2025, after the previous explosion at the same site in July 2024, captured a dark-colored steam plume jetting out of the ground north of the pool. When park rangers went to investigate, they noticed something wrong with the Firehole River. The water flowing downstream from Biscuit Basin was light gray and milky, a sign that large quantities of sediment had been discharged into the river from the explosion site. Geologists arrived the next morning, June 14th. What they found was a transformed landscape. 3 separate vent groups had opened. The northernmost was a crack 18.5 meters long, 61 feet, and up to 1.5 meters wide in places, running northwest from Black Diamond Pool. The water inside it was 90 degrees Celsius, 194 degrees Fahrenheit, just below the boiling point at that elevation. Rocks that had been ejected during the explosion were scattered around the crack. A middle group of 5 smaller vents had produced short-lived water flow before ceasing. A southern vent, 49 feet in length, had sent significant water and sediment directly into the river before stopping within hours of the explosion. Stop for a moment. The geological team was walking across that ground on June 14th, mapping the vents, documenting the fissure, recording temperatures, and then they came back on June 16th. The ground they had walked on 2 days earlier had collapsed. In its place, an actively boiling pool had formed, 6.5 meters by 5.3 meters in size, gray and silty, with no surrounding debris to indicate an explosion had caused it. It had formed by collapse. The subsurface beneath that spot had given way. The team described the pool as producing notable thumping sounds, the sound of steam bubbles forming and then collapsing within boiling water, that startled the geologists when they approached. On June 18th, 5 days after the original explosion, the new pool began intermittent spouting, shooting water 20 to 30 feet into the air and roiling vigorously between episodes. This is a new permanent feature of Biscuit Basin. It did not exist on June 12th. It appeared beneath the feet of scientists who had been standing on that exact ground 48 hours earlier. This is the second hydrothermal explosion at Biscuit Basin in 23 months. The July 2024 event sent mud, rocks, and boiling water 400 to 600 feet into the air while park visitors ran for their lives. A boardwalk was destroyed. The area has been closed since. The June 2026 explosion was smaller. Ejected rocks traveled only a few meters, but it occurred in ground already destabilized by 2024, opening new fracture pathways through rock that had not previously been broken. The USGS notes something specific about the June 2026 explosion that makes it scientifically unprecedented. No hydrothermal explosion has ever occurred this close to an active monitoring station. The event happened 328 feet from the Biscuit Basin monitoring array installed in 2025. If there were seismic or infrasound precursors, signals that appear in the data before the explosion itself, this is the first time scientists have had instruments close enough to capture them. Reviewing that data is now a top priority for the Yellowstone Volcano Observatory because identifying precursors to hydrothermal explosions is one of the most consequential unsolved problems in Yellowstone science. Why? Because the geological record beneath Yellowstone contains evidence of past hydrothermal events that dwarfed anything recorded in modern history. Mary Bay, on the northern shore of Yellowstone Lake, is a crater 2.7 kilometers across, left by a hydrothermal explosion roughly 13,800 years ago that ejected material with the force of a small nuclear detonation. The rock record at Yellowstone contains dozens of similar craters. The June 13th event was not in that category. USGS scientists have been clear. Current data shows no magma movement, no unusual uplift, no volcanic precursors. Yellowstone's alert level remains at normal. A hydrothermal explosion does not indicate an imminent eruption. What it indicates is exactly what the USGS said, the dynamic and hazardous nature of Yellowstone's thermal areas. But here is what the June 2026 data is actually telling seismologists who study this system. In June alone, the University of Utah seismograph stations recorded 118 earthquakes beneath Yellowstone. 3 separate swarms occurred, 25 quakes from June 6th to 9th, 20 quakes from June 22nd to 25th, and a third smaller cluster between them. The largest was magnitude 2.4, individually unremarkable. But together, with 2 hydrothermal explosions at the same location in 23 months, they describe a hydrothermal system actively opening new fractures, finding new pathways, redistributing pressure through rock in ways monitoring equipment is only now beginning to capture. The June 13th explosion is, in Michael Pollan's words, an unprecedented opportunity. The closest monitoring station ever positioned to a real hydrothermal explosion recorded data scientists have never had before. What it reveals about warning signs or their absence may fundamentally change how the park manages safety for 4.5 million annual visitors. The new boiling pool at Biscuit Basin is still there, still spouting, still roiling, still hot. It is sitting on ground that scientists walked across on June 14th, unaware that the earth beneath their feet was about to collapse into something that didn't exist 24 hours before. That is what Yellowstone does, not with warning, not on a schedule, on its own terms, in its own time, on a geological clock that measures in pressures and temperatures that humans have been studying for decades and still cannot fully read. The question scientists are now poring over is whether the data from June 13th will finally let them read it. The answer to that question will come from the monitoring station that was standing 328 feet away when the ground opened up and no one was watching. Subscribe to Seismic Alert. We will be watching.